I'm sitting between two moving objects that don't seem a lot like each other. I have a simple pendulum, which is a large mass at the end of a lightweight string. And I just have a couple of 200-gram weights hooked up to this spring. But what they do have in common is that they're repetitive. They're going back and forth. And this kind of repetitive motion is worth studying, not least because it can be used to keep time. I'm sure you know that some of the earliest clocks used pendulums in order to keep time. And the most important characteristic of anything going back and forth, especially if it's perfectly repetitive, is its period. The time it takes for a complete back and forth. So the way you find that is you pick a spot in the motion, you call it the starting point, and you figure out the time it takes to go from that spot to the other side and then back. So let's do that with this pendulum. I'll put my finger over here, and I'll just say back, forth, and I'll do that for several repetitions. So back, forth, back, forth, back, forth, back, forth, back, forth, back, forth, back, forth. You could probably hear from the cadence of my voice that the period, the time it's taking for a back and forth, doesn't seem to be changing. It seems relatively constant. Is that true over here? Well, I'll try that. I'll start with down. So down, up, 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 down, up. It has its own period. Time to go from down to up and back to down. It's different than the pendulum. In fact, we're going to see every pendulum and every mass on a spring has its own unique period. And that's what we're going to start investigating in this unit. What factors cause this? These are both types of a very interesting type of repetitive motion called simple harmonic motion. It results from a very specific relationship between the force used to make something come back to where it was and the location of where it is. And believe it or not, these two objects have that rule in common, which we'll discover in the course of this unit. So what leads to this kind of periodic motion? We got to think about what kind of functions might be involved in describing the position, velocity, acceleration of those objects as time passes. Let's start with the mass on a spring that was going up and down. I'm going to emulate with my hand going up and down what it would look like if a piece of chalk was on that mass. Just going to walk towards the other side of the board. So I hope that sort of looks familiar to you. When I have the back and forth motion suddenly have motion in one direction, it starts to look like a sine or a cosine graph. We're going to see sine and cosine are very helpful in describing this type of back and forth motion that we're interested in. So what I did there is I basically took the back and forth, and by adding a little motion, I showed how position changed with time. And it appears to be roughly sinusoidal. Let's see if we can come up with a mathematical justification on how sines and cosines could be used to describe this type of back and forth motion. We'll start with a mass on a spring. We'll have it going back and forth like this on a frictionless table. The reason that's easier is, of course, gravity is down. We have an upward normal force. But they're not in the same dimension as the spring force. So just to keep things simple, we'll have the spring force be in its own dimension. Let's say I give a little push in this direction. So in other words, I'm displacing a distance x. What's the spring going to do? It's going to fight me. The spring force will be back the other way. What if I pulled the mass this way? The spring's going to fight me too. Then Fs would be back the other way. So What I have here with the spring force is actually called a restoring force. Whatever direction I displace it, change its distance, it gets a force back in the opposite direction. So let's look at how a restoring force shows up in a sum of force equation. If we write the horizontal net force equation for this situation, clearly it's only Fs. We should be a little bit careful with what equation we put in for Fs here, because we know we can call it Kx, the spring constant. Up until now, we've been pretty lenient about saying you could call either left or right positive or negative as long as you're consistent. We have to be super careful here, because we have to be consistent not just in terms of forces, but in terms of accelerations and distances too. So if we take this as the example, I'm pushing that way, left. The force is back that way. So the force is going to cause an acceleration, and that acceleration is in the opposite direction of the way I pushed it. So there needs to be a negative sign here. And that's a trademark of a restoring force. This is telling me that x is proportional to a, but not just a, the opposite of a. That's a huge deal, because x and a have a relationship. If you have a position function, x of t, and you want to get the velocity function, what's v of t? Well, we know we take the derivative. What if you want the acceleration function? Well, that would be the derivative of velocity, or it would be the second derivative of position. So we have a relationship between acceleration and position. So I could rewrite this as minus kx equals m d squared x dt squared. So when you have a restoring force for the kind of periodic motion that causes simple harmonic motion, you have this type of relationship where you are is directly proportional to the second derivative of where you are. And this is going to be at the start of most of our calculations. So what kind of functions is this true for? That's what gets us back to the idea that sine and cosine might have something to do with it. If you have x equals sine theta, v would be dx dt, and we know that the derivative of sine is cosine. And if you have a, which is dv dt, we know that the derivative of cosine is negative sine. Guess what? directly proportional to our position. So the function that describes where you are very well could be a sinusoidal function. Something that we could then go ahead and sub in here and there. That will seem complicated at first, but when you see a bunch of these, you'll see it's very repetitive, and it always goes the same way. So that's the end of this video. What I'd like you to watch now is a video produced by Drs. Ivy and Hume called Periodic Motion, which is going to justify this graph a little better, showing that simple harmonic motion in a situation like this really can be described by this graph. Then we're going to come back and we're going to look at how we can use sigma f equals ma and sub in a trig function for both x and a, or d squared x dt squared, and come up with an equation for period for that object. Just so you know, sigma x equals ma can be one of the two equations we start these calculations from. The other one can be the rotational version. And that would apply for motion that, instead of being in a plane, is motion that involves twisting or rotating. The arguments go very similarly because theta and alpha have the same relationship, x and a.